Okay, it's 6. Shall we get started, folks?
Sure.
Okay.
Sure.
Okay. Hello, everyone. Welcome to join us. This is our third seminar of our one word signal processing seminar series. And it's our great pleasure and honor to have Professor Piya as our speaker today. So Piya is no stranger to many of us. Personally, I actually got to know Piya's name even before I started my PhD study 10 years ago. Among the papers, the first batch of papers that my PhD advisor mentioned to me, there was Piya's early work on the nested array processing. So I learned a lot from her work. So Dr. Pao is now an associate professor of electrical and computer engineering at the University of California, San Diego. She is also a founding faculty of the Holly Jolo Data Science Institute. She obtained her PhD degree in electrical engineering from Caltech in 2013. And her research interests include the signal representation and the sampling for high-dimensional inference, super-resolution imaging, convex and non-convex optimization, and the statistical learning. Her research has been recognized by a lot of prestigious awards, including her PhD thesis. Her PhD thesis won the 2014 Charles and Alan Wheats Prize for Outstanding Doctoral Thesis in Electrical Engineering at Caltech. Her research was also awarded the very prestigious Presidential Early Career Award for Scientists and Engineers, the PCAS Award 2019, and also the 2019 Office of Naval Research Young Investigator Program, ONRYIP Award, 2016 National Science Foundation Career Award, and several student paper awards with her students. And Dr. Pao also contributes a lot to the society by offering her service work. She is an elected member of the IEEE Sensor Array and Multi-Channel Technical Committee, the IEEE Signal Processing Theory and Methods Technical Committee, and also the EuroSIP Signal Processing for Multi-Sensor Systems Technical Committee. And she is currently serving as an associate editor for IEEE Signal Processing magazine. So without further ado, I will just pass the microphone to Dr. Pao. Piya, the floor is yours.
Thank you, Sheo, firstly for the very gracious invitation, for the kind introduction. You guys have done a very good job of organizing some very impressive talks. The first talk was by Georgios. I attended the second half of it because I was teaching before that. It was amazing. Then the second talk was by Wahid, also I really enjoyed it. And finally, today is my chance to speak. So I hope that I can basically give you some take-home messages about super resolution, which is a old and a new topic. So my talk today is going to be about some of my very recent works actually on this topic of super resolution. The super resolution is a classical topic. It has been studied in sensor array signal processing for a long time, although it has its origins in optics. Recently, from a convex optimization point of view, this problem has been analyzed mathematically and giving some very unique insights about the problem, about the geometry of the problem rather. I will tell you where my research fits in the middle of all these classical and modern methods and what is a new message that I am trying to convey through today's talk. Okay, so just to make you aware, the key idea here in the title is the spatiotemporal measurements. Okay, so I will try to argue that when you have spatial and temporal measurements, then there are some underlying trade-offs that happen. And if you can exploit the structure of both spatial and temporal measurements and perhaps trade one for the other, you can actually enhance the super resolution performance by quite a bit. So I will try to establish this mathematically in today's talk. So let's try to first, so this is the outline of my talk. I will first try to give you some background and motivation why super resolution problem is interesting, where it features. Then I will talk about the so-called discrete version of the problem, which is concerned with sparsity. And this discrete super resolution is especially relevant when your goal is to actually display a super resolved image on a pixel grid, right? That the problem is inherently discretized. So the discretized problem has similarities with the continuous counterpart, but there are also essential differences. So they have to be treated slightly differently. Then I will go to the continuous version of the problem, which is also known as the gridless version or off the grid. It's basically super resolution off the grid, where you actually convert super resolution problem to a parameter estimation problem. Okay. And in both cases, I will argue that exploiting temporal measurements and statistical priors judiciously will give you provable advantage. And I will establish this both from the classical algorithmic point of view and also using modern tools of analysis that has been widely used these days. So first, some background and motivation. Just want to make sure there is, okay. Yeah. So the goal of super resolution is really, roughly speaking, recover lost details, typically which are high frequency components of an unknown signal, from noisy low resolution measurements acquired by a physical imaging system. Okay. So the word lost is in quotes because if it is really lost, you cannot really recover, right? But however, in most cases, you are not really trying to recover something which is completely lost. Either it is folded back into the measurement in a certain way, okay, creating aliasing or creating certain ambiguities, which makes it harder to find it, but not impossible. In some other cases, those frequency components may be completely lost, okay, because you may have a very strict low-pass filter, which kind of filters out the high-frequency components. In that case, your goal is to guess what those components might have been. In such a case, if you know something about the image, like sparsity or some low-dimensional representation, that can really help you recover the lost components. So the problem essentially has its origin in optics. And I have, along with my colleagues in optics these days, I have actually started looking back at some very old and very fascinating literature in optics. I don't think I'll get a chance to talk about them today, but maybe some other at some other discussion we can have a closer talk about this. They have some very clever techniques that people did a long time back, and it is a very good idea to go back and try to analyze what they did using today's modern tools. So this problem actually features across many applications, such as radar, microscopy, medical imaging, radio astronomy, and broadly in image processing computer vision. You know, there is this problem of single image super resolution, multi-image super resolution, and so on and so forth. You also have super resolution neural networks, the ResNets, which also try to super resolve images. So traditionally, this problem has very close ties with the so-called harmonic retrieval problem. And sometimes people even try to cast a super resolution problem, which arises from different kinds of point spread function, into its harmonic retrieval counterpart by casting the problem from the space domain to the frequency domain. Okay, so I will go into that derivation a little later. So the goal in super resolution is really, do you have a model like this? You have a bunch of harmonics, okay, with frequencies omega1 to omega k, and either you receive directly this kind of measurement, or your measurements can be converted to this form, okay, by casting it in the frequency domain. There are some trade-offs there. It is not straightforward, but suppose this is true. Suppose this is the model that you start with, and NM represents noise. So this problem, like I said, has its origin in classical array processing literature. Harmonic retrieval, line spectrum estimation, goes by many names. The classical methods are primarily algebraic, okay? So it tries to exploit the fact that these complex exponentials give rise to Vandermonde vectors on the unit circle. And using properties of the Vandermonde vector, using the unique property of the subspace spanned by these vectors, it tries to develop low-rank matrix factorization-based methods to isolate the frequencies. So there have been a lot of classical work on this topic since decades, many, many decades, very influential works from which we can still learn a lot. This list is by no means exhaustive. I apologize if I have missed some of the references, but it's just impossible to cite every one of them. So I just highlighted a few. The one thing to note about this classical techniques is their guarantees are mostly asymptotic or perturbation based. So they kind of look at the nominal model to understand the effect of noise. They assume there are small perturbations around the nominal model, and then they try to see how the eigenvectors and eigenvalues get perturbed, and then they derive their error bounds based on this perturbation. So this perturbation analysis is useful, but it is primarily asymptotic in nature. Only small perturbations can be analyzed this way. There are recent advances, though, however, in these classical methods, and I will encourage you, or I will be happy to kind of talk more about these if you're interested offline, by primarily from mathematics community and harmonic analysis community, who try to analyze these classical methods using tools from basically interpolation theory, okay, polynomial interpolation theory. If you can construct certain kinds of interpolating polynomials, you can prove stability guarantees of these classical methods, subspace-based methods. And one of the early works in this regard was done by the single snapshot music performance guarantee by Wenjing Liao, who's at Georgia Tech right now. Then there was a paper by Ankur Moitra from MIT back in 2015, and he has a very recent paper in 2020, excellent paper. I was actually going over it, where he actually analyzes the effect of this airy diffraction limit, airy functions, point spread functions, airy disks. And then by Wei-Lin Li, who's at NYU, he also has a recent paper in IT transactions, which derives stability guarantee of Esprit type techniques, and some of my own works that I will talk about today. Now, separate from this work, there are modern convex algorithms for super resolution, which are based on atomic norm or TV norm minimization. So these methods are convex. So, there are, you can have provable guarantees. You can analyze these techniques. There are solvers available to solve these problems. And using that for the framework of convex algorithms, there has been a series of work pioneered by Candace and Fernandez Granda, followed by Gongguo Tang, etc. So this is another line of work. So this is in a very nutshell, this is the state of literature in super resolution right now. Now, where does my research fit in? I'm especially interested in the problem where you do not have a single measurement or a single image to super resolve. You have a sequence of images, okay? And this is very relevant in optics. If you look at algorithms such as STORM or PALM or let's say SOPHI, these are specific algorithms which are very famous in super resolution microscopy. And STORM actually because the inventors of STORM won the Nobel Prize in 2014 in chemistry. So they actually take a sequence of images. How do they acquire these images? How do they generate this kind of control the illumination? There are a lot of technicalities there. However, you do not perform super resolution based on one image. You gather a sequence of images and you do some kind of a processing. In many cases, you actually look at the correlation, inter-image correlation, or even correlation between pixels computed across the time, and then super resolve the image. Okay, and these are very relevant not only in microscopy kind of applications, but also in radar, because typically we collect multiple snapshots to do source localization. Okay, so if you have such a setting, it is quite interesting to understand how the temporal and the spatial measurements can be traded off. What is the underlying trade-off? Is there a trade-off, firstly? If there is a trade-off, what is the best way to exploit one for the other and gain resolution? So people in optics know this, that you can actually, if you acquire more measurements, it should, in principle, it is very natural to assume that it will lead to enhancement of resolution. But mathematically underpinning to what extent you will gain, this is a very important question, okay? And I will try to give some answers to this question, but it is a continuing effort. All right. So, in addition to collecting several measurements in many applications, especially in this microscopy kind of applications, the sources are assumed to be spatially incoherent or statistically uncorrelated. So basically, if you have these fluorescent molecules, their fluctuation over time can be statistically uncorrelated. One molecule will fluctuate in an independent way compared to the other. Is there a way to exploit this statistical prior? Okay. So in my prior work, I actually exploited the fact that certain sources, two distinct sources from two different spatial directions, are statistically uncorrelated to come up with sparse array geometries. So I actually say that if you have this kind of priors available on your scene of interest, you can actually be smart about how you are sensing the environment, okay? You should not put an array in a uniform geometry. If you have a fixed budget of sensors, go ahead and organize it in a sparse way, in a structured sparse way, not randomized, but in a structured sparse way. So, and these gave rise to certain geometries, which are called nested and co-prime arrays, among others. And these kind of arrays, along with minimum redundancy arrays, which was widely known by earlier works, it is widely known even earlier in coding theory, Golomb ruler and all that. But even in the context of array processing, by work by Moffett, Pillai, Salim Qasem, Yuri Abramovich, etc., they realized the importance of minimum redundancy array. But minimum redundancy arrays have it is not possible to get analytical closed form for those geometries. So this is where the sparse and co-prime array comes and fills in that gap. They are analytically tractable, and they can be designed using very simple concatenation of uniform linear arrays. You do not need to kind of do any sophisticated calibration, okay? And yet they do the job. They're order-wise as good as minimum redundancy array. So the main idea here is, because you have this correlation priors, the sparse arrays allow you to generate what we call virtual measurements, okay? So as you compute correlation between sensor pairs, new baselines or new virtual sensors pop up. How do they pop up? Through statistical averaging, okay? So if you average more using more temporal snapshots, the estimates of these virtual measurements become better and better, okay? So there has been a lot of analysis in recent times on the statistical performance of these sparse arrays, although many questions are still open. However, asymptotic guarantees are there for resolving more sources and sensors, okay, using perturbation kind of analysis. And it is shown that it has significantly smaller Khatri-Rao bounds, sparse arrays, compared to ULAs with the same number of sensors, everything being the same, only the geometry being different. You can actually reduce the Khatri-Rao bound. So what is open? Non-asymptotic guarantees are largely open. So if you do not do this, if you move away from this small perturbation-based analysis, and if you actually want to understand with a finite budget of snapshots, with a finite SNR, everything is finite, can I get sharp guarantees? So I will show you progress towards this question, and we will also, and this will again open up many more interesting insights about this problem, because the main issue is, you see, the sparse arrays enable us to operate in a parametric regime where classical analysis has not been done. And also the modern techniques based on TV norm or atomic norm minimization, they do not operate in this regime. So there are many open questions that you can ask regarding the performance analysis in such a regime where the number of sources are more than the number of sensors, or two sources are coming very, very close to each other, much, much beyond the Rayleigh resolution limit. Can I still have some notion of stability in such a setting? These are the type of questions I'll try to answer. And what role do temporal measurements play in such a case? Okay. So these are the primary questions of interest. Can correlation priors and aperture synthesis provably lead to improvements in resolution? And as is well known, that TV and atomic norm-based algorithms require some minimum separation between sources. So their stability guarantees and robustness guarantees are all based on assuming that two sources are separated by a minimum distance. If that minimum distance condition is violated, there are no guarantees currently, okay? And the reason is because the way these guarantees work is by constructing an interpolating polynomial, okay? Construction of such a polynomial will fail if you do not have this separation. That is the main reason. So the proof technique will fail. However, so that is the current status of atomic norm TV norm minimization algorithms, especially in presence of noise, okay? Presence of noise is very important because noiseless super resolution can be done. Noisy super resolution is the main question. So the point is, the strict separation, which is almost the same as the Rayleigh resolution limit, can we relax this fundamentally? Because honestly, that is the goal of super resolution, to go beyond Rayleigh resolution limit, to go beyond diffraction limit. And noise, and in the process, can you also reduce the noise amplification that inherently happens in super resolution by exploiting three things: the sensing geometry, additional temporal measurements, and there is inherent structure in the problem. There are conic constraints, because when you cast the problem using correlation, you can have certain kind of positive semi-definite conic constraints that you can impose on your problem. They are very helpful. Okay, they can be super helpful if you exploit them properly. So that's the case that I will try to make today. So first, we will look at the discrete version of the super resolution problem, which is concerned with reconstructing an image, okay, of a certain size with higher resolution grid. So this discrete version of the problem, basically, you are given a coarse low resolution image, let's say, acquired by the physical sensing device, and you want to reconstruct an image which is defined on a higher resolution, finer grid, okay, finer grid. In this case, for example, I am showing this image on a 4 times scaled up grid, but it is not a simple upsampling, okay? Simple upsampling won't cut it. It will not get rid of this blurriness, of course not. So the goal is to actually somehow invert the effect of this blurring kernel, and obtain the super resolution estimates of these sources. Clear? Basically make the image very sharp. Now you can say, is it the same thing as deblurring? No, there are subtle differences. In super resolution, the kernel is very ill-posed. So you cannot just invert the kernel or say I'm deconvolving. Deconvolving is an unstable process in super resolution because the kernel is non-invertible. The kernel is non-invertible because it has sharp cutoff frequencies typically, and it completely blocks off high frequency components. So if you try to deblur with such a kernel, it will give rise to noise amplification. So it is a very challenging job actually to do super resolution with such a kernel. Now this idea of taking low resolution measurements collected by a sensor array, CCD array, let's say, and creating a higher resolution version of the image is very common in super resolution optical imaging. Okay, these are some recent resource references which also use the correlation prior. Now, the discrete version of the super resolution problem actually has been thoroughly studied, and the very pioneering work is by Donahoe in 1990 in his paper by super resolution with sparsity constraints. So there he actually studies the effect of noise on super resolution in the discrete setting. Okay, and like I said, the discrete version appears frequently in applications where the goal is to basically display a super result image in a high resolution pixel grid. Now, what is the measurement model? So the measurement model is y equal to q times x plus n. Q is y is your measured signal, measurements basically. Q is a discrete convolution operator. It represents a low pass filter, okay? So in the discretized version of the problem, you can think that Q is basically the frequency, the DFT coefficients of Q are given by lambda, okay? And lambda becomes 0. The elements of lambda, the lambda is a diagonal matrix because it is diagonalized by a Fourier DFT matrix. It's a circular convolution because we are working with finite length signals. So, so your the frequency domain, the DFT coefficients of Q becomes 0 after a certain cutoff frequency. And this is exactly why the problem is difficult, okay? So Q is actually a low rank matrix, strictly low rank. The rank is determined by FC. And your goal is to recover X from this kind of a measurement, from a low rank Q. Okay, so you can immediately see null space of Q will create problems if you try to reconstruct this X from Y. And Q, not only that, Q is not a random matrix, Q has structure. Okay, Q has structure. So it is not like we can just plug and play compress sensing algorithms here. And I am also not allowed to take randomized measurements in frequency domain. I cannot because this filter has a sharp cutoff. It goes to 0 beyond a certain cutoff frequency. So just to make you aware that there are distinctions between regular sparse compress sensing kind of problems and super resolution. So this is X is a desired high resolution signal. Now you can represent the frequency domain by just multiplying Y with W, and you get this kind of a representation. So if lambda has a flat spectrum, so let's say all the frequency components, all the DFT coefficients are roughly the same within the band, then this problem becomes the same as reconstructing a signal from its low frequency DFT measurements, okay? Lower DFT coefficients. You have no clue what the high DFT coefficients was of this X because it has been cut off by the filter, okay? So you can see that unambiguous and stable recovery of X and from Y is not possible unless we exploit priors. It could be anything. You could just arbitrarily pick vectors from the null space of Q, and they could be potential candidates unless you know something extra about X. Okay. So this is where the use of priors come into play. So suppose let's C denote a class of signals that desired X belongs to. C captures the prior information about X. So the point is, if you're given this kind of a prior information, then we call a super resolution technique to be stable if it produces an estimate X hat of X such that the error in the super resolution reconstruction is less than or equal to some constant. This constant is not a universal constant. It's very important to note it here. Some constant times the norm of the noise. Okay. So this constant is called the noise amplification factor. So basically, the measurement noise get amplified by this factor. And this is how the error in the reconstructed signal gets blown up. So if this noise amplification factor is large, then you have really severe noise amplification. And it really depends on your algorithm that produces your X hat, right? How much the noise amplification will be. Now, this noise amplification definitely depends on capital N. Capital N is the size of the high dimensional grid that you're trying to reconstruct the signal on, okay? And as you will see, as you try to reconstruct the signal on a finer and finer grid, you lead to noise amplification. And this noise amplification can be pretty bad, okay? Yeah. So now we are trying to see what kind of a priori information can we exploit. So suppose we assume that this signal is non-negative. Positivity. This is one of our prior information about X. Can this prior information enable stable recovery? So this is the only information about X that you're going to use. Okay, you're going to use in your algorithm. Your algorithm knows that the signal that you're trying to reconstruct is non-negative. So it seems like very interesting question. You don't even have to know it is sparse or not, just non-negative, okay? So this question was asked recently, relatively recently, 4 years back, by Morgenstern and Candace. Their paper called Super Resolution, basically positive super resolution discrete setup. So here, look at the problem that they're trying to solve. They're trying to minimize basically the fitting error y minus qz, okay? Subject to non-negativity constraint. No explicit sparsity constraint is enforced. Nothing, no TV norm, no L1 norm minimization, nothing is happening, just this. In a remarkable way, they show that stable recovery of X is still possible if X is non-negative and it satisfies something called Rayleigh regularity. So what is Rayleigh regularity? So Rayleigh regularity, the definition is a little bit complicated, but I will try to explain it informally here. It simply means how many spikes the signal contains. So the signal is the true signal is sparse. You're not using its sparsity, but suppose your true signal is sparse, okay? So the support indices of your true signal, the indices of non-zero elements, they should not be clumped up together too much, okay? They should have some separation. But it doesn't require a strict separation between two non-zero indices. What it requires it that over a certain length, okay, certain interval, there are not too many spikes. So this Rayleigh regularity has two parameters, D and R. So it should not contain more than R spikes in D consecutive intervals, each of length 1 over FC, and FC is the cutoff frequency of your filter. That's called Rayleigh regularity. So if you have Rayleigh regularity with these parameters, 3.724 RR, these are technical conditions to basically construct an interpolating polynomial, then, and the Q filter has a flat or triangular spectrum, okay? Either it is flat or the frequency spectrum is triangular. Then the solution to that very simple problem, which does not even enforce any sparsity constraint, will give you a stable answer. And this we owe to non-negativity, okay? This we owe to non-negativity. However, the noise amplification factor will be of this kind, n over m to the power 2r. This m is the number of low frequency measurements that you collect, and n is the size. N is the maximum high frequency DFT maximum index of the DFT coefficient that you want to extrapolate. So the more you extrapolate, the more it gets worse. And the more spikes are clustered, R is a measure of how many spikes are there in a certain interval. Again, it becomes worse. It's a very intuitive result in that sense. And when you have strict separation between two spikes, which means two spikes are separated roughly by 1 over m, okay, some constant time divided by m. This is reminiscent of Rayleigh resolution. Then the noise amplification, noise amplifies by a factor of n over m squared. And this is the super resolution factor squared. This is very well known. So you will see this kind of noise amplification happen over and over if you look at the literature of TV norm or atomic norm minimization, and when they try to extrapolate the signal to a higher frequency component, okay? And this, you can imagine why this happens, because we are essentially trying to estimate a lot of unknowns from only M measurements, right? So you're trying to estimate what, up to nth DFT coefficient would have been. So if you do such a thing, you'll incur some error, and this error propagates as you want to extrapolate to larger and larger images. This is the main reason why error amplification happens. Now, in our case, what we will do is, like I promised, we will consider L snapshots of the image. So we are not considering just one spatial measurement, we are considering L spatial measurements. And in particular, what we will do is we will introduce some correlation priors. We will assume that the source amplitudes are statistically uncorrelated. And like I said, this assumption is very, very common in optics literature. Although I started off with this kind of assumption in the context of array processing, I was very pleasantly surprised to see how common this assumption is in optics literature, where the statistical fluctuation, independent fluctuation of the sources are heavily utilized actually for super resolution. They knew this. It's very, very, very nice to see this unifying trends. So goal of correlation-driven super resolution imaging is, yes, you're trying to reconstruct an image on a higher pixel grid, but you're trying to actually estimate the power at each pixel, the source power. Okay, that is the goal. So you collect all these aggregates over time, and you get some sort of an empirical estimate of your source powers, and the source powers is what you plot in your image. Okay, so we are actually interested in clearly in a non-negative image, in an intensity of the power image. Now, utilization of correlation priors can lead to significant improvement in super resolution performance. And this has been recently shown in this paper called SPARCOM by Solomon, Eldar, Mutsafi, and Segev from Technion. So these are from optics community, actually. So, sorry, excuse me. Yeah. So what happens is, if you look at the correlation of your measurements, so you collect, let's say, several snapshots. Suppose you had access to the exact covariance. We will relax this condition in a moment, don't worry. But I'm just saying that suppose somebody gave you the exact ideal covariance of your data, okay? What can you do? If you now try to understand this, P is your desired power image that you're trying to estimate, and it is related to your correlation or the covariance matrix of your measurements through this map, which is the Khatri-Rao product of A with itself, A conjugate with itself, okay? And remember, A has a Fourier structure, okay? A has a Fourier structure. So this Khatri-Rao product leads to something very interesting. So what happens is, if you really look at how the elements of this column-wise Kronecker product behave, you will see that if your sensors are located at locations D1 to DM, what shows up in this Khatri-Rao product is their difference set, pairwise differences, okay? So you take pairwise differences between sensor location pairs and you consider a difference set. So for example, let's say your sensors are located like this. So, some of your sensors are clustered together and the remaining ones are kind of spread out. This is called a nested array, but just imagine that your sensors are like this. So your difference set, what happens is, if you take pairwise differences, all these skipped elements get filled up. Okay, get filled up, and you can generate a very dense virtual array. And these virtual array acts as extra virtual measurements, which, if you have reasonable number of snapshots or good estimates somehow, okay, of this correlation values, then you can use them to attain super resolution. Okay, that's the main idea. So MDiff will be called the large cardinality of largest subset of consecutive integers. Consecutive integers are important to prove our guarantees, okay? So if they are non-consecutive, the guarantees won't work so well. So we call this cardinality of the largest subset of consecutive integers in DS, which means there is no missing virtual elements, okay, in that range. And this quantity, I will claim, will play the most critical role in determining what you can or cannot do in the discrete super resolution case. So if you again go back, I'm trying to recover this P, which is a very large, the diagonal of P basically, which is a very large vector. A is a fat matrix. Remember, A is a fat matrix because you are doing super resolution. Now, can you actually recover P, even if somebody gave you the ideal covariance matrix of your measurements? Can you recover P from there? Because it's not obvious, right? Because A is fat, A is not tall. So you may, this is reminiscent of standard error processing, but it is also different because A is fat. And A doesn't have, you cannot randomize the rows of A or anything. They are what they are, okay? So the point is, yes, you can, and you do not even need to know the sparsity pattern of P in that case. When without knowing it, you can, it is uniquely, this P and sigma both, you do not even need to know the noise power. P and sigma both can be uniquely identified from the covariance. There is a unique map from P sigma to RYY, okay? And this is we call it a warm-up result because this is really if you had the covariance matrix. But I thought the proof was quite interesting. The way we kind of designed the proof is we show that firstly, there is no need for separation. If you have enough temporal measurements, there is no need for separation, explicit separation that, okay, the sources have to be separated by 2 over m or c over m, okay? At least if you have the ideal covariance matrix. And explicit sparsity constraint also not necessary. And let me tell you, in non-negative compressed sensing, several years back, maybe more than 10 years back, people had noticed that sometimes when you have non-negativity constraint, you get uniqueness for free in certain kinds of measurement systems. Okay, there was a very interesting line of work by a very niche group that actually showed that non-negativity constraints can lead to uniqueness. And there were some follow-up work. So this problem also has a similar flavor, this result. And the proof technique is basically to take this RYY, lift it to a higher dimension, construct a Topliss matrix out of it, and invoke Carathéodory's Vandermonde decomposition, which says that a positive semi-definite Topliss matrix has a unique Vandermonde factorization. And that is exactly where using that unique Vandermonde factorization, you can actually identify the non-zero indices of P uniquely, even without knowing the sigma square or the sparsity. So it will be rank revealing in some sense. Okay, so that's the main idea. So inspired by this idea, now let's look at what happens if we have finite snapshot error. Okay, so still can we use the positivity of the correlation image and the geometry of the sensing to get stable super resolution? And in the process, can we relax the separation condition? And hopefully, let's see if we can also lead to reduction in the noise amplification or error amplification. So here, error amplification will have a different flavor because we also have error due to correlation estimation. Okay, so because you have finite snapshot estimation error, you have to count them in. You not only have noise, you also have this kind of finite snapshot covariance estimation error. So we have to be mindful of those as well. So suppose, in order to understand if this problem is again, hopeless or not, okay? Because we have noise now, not just, ideal covariance matrix. So let's try to understand the geometry of this set. So this set is actually an interesting one. You basically look at all vectors Z, again, this A Khatri-Rao A is again a fat matrix. It has grown in the number of rows, but it still can be fat. And I will consider it to be fat. I will operate in a regime where the grid is fine enough. So this matrix is fat. So if this is fat, you're trying to look for Z, which satisfies non-negative constraint and is within this error ball. So this is the covariance estimation error. And later on, of course, we will develop statistical guarantees. For right now, let's condition on given a covariance estimation error delta L, let's define this set, okay? Now this feasible set is of course characterized by snapshots L because this error bound will shrink as L increases, and it always contains the true source power by construction, okay? Now, sorry. Wait, I think it went out of full screen mode. Let me go back. Yeah, sorry about that. So the point is, can I bound the distance between any 2 points in this set? Okay. I'm not using sparsity. So if I had also assumed sparsity, then that would lead to something like RIP, right? Can I bound the distance between any 2 sparse vectors which satisfies this error bound? That will lead to RIP, but I'm not asking that question. I'm not saying that I want to bound the distance between 2 sparse vectors that lie in this set. No, without using sparsity, just by using positivity. And with this very structured A, can I bound the distance between 2 points in this set? Okay. And of course, this distance will depend on delta L. Clear? Of course, when delta L is 0, we have seen that this set shrinks to 1 point. 1 point. Okay, so is there a hope that even if there is noise and this set grows, estimation error and so forth, does the set still remain bounded? Why is this challenging? Because Khatri-Rao A has a null space, and the null space can actually, you can select points from the null space of A and add this to any point Z in this set and make their distance become unbounded, because null space is a subspace, right? So what can prevent such a situation? This constraint, positivity. Why? Because it will make the overall set bounded by intersection of this cone and a subspace. Okay, this is the main idea. How does the conic constraint help? So I'm trying to draw here intersection of a cone and a subspace, but it's kind of interesting to kind of generate these kind of figures. I had some fun doing that with my students, of course. So the point is, if you did not have this non-negativity constraint, like I said, you can take a point P from this set. There is a point because the true P is within this set by construction, and add any vector from the null space of A Khatri-Rao A, it's a Khatri-Rao product of A to it. And then the distance between these 2 points can be made arbitrarily large, because you can choose whatever alpha, it will still belong to the null space, right? I mean, this P plus alpha B will still satisfy this constraint, as long as P satisfies this constraint, right? Because A times V will be 0. A Khatri-Rao A V will be 0. So this is the reason why without positivity constraint, you cannot bound the distance. But with positivity constraint, you can. And this is the main result, okay? So we actually, to state our main result, we introduce this notion of a relaxed difference set separation condition. So typically separation condition is some constant over M, where M is the number of sensors, okay? However, in this case, our separation condition is some constant, in this case 2, let's say, over M diff. And M diff is the size of the difference set, not the size of the physical, not the number of sensors in the physical array, is the size of the difference set. The consecutive integers in a difference set. So sometimes the difference set itself can only consist of consecutive integers, as happens in the case of nested array. So in this case, it will be the size of the difference set itself. And this phi is nothing but a wraparound distance, okay? Because we are looking at phases. So the phase is periodic, right? So that is why it's a wraparound distance. So this is one of our results, that suppose your ground truth, the P that was generated, satisfies this relaxed difference set separation condition, the sparsity pattern of P. And P is also non-negative, which is true because it's a power, right? Source powers. Then for any P sharp, which belongs to that feasible set, okay, we can always bound the distance between P sharp and P by the correlation estimation error scaled by this factor 1 minus rho over rho. And rho is nothing but M diff over N squared. So this factor is roughly proportional to 1 over rho. So this is like N over M diff squared. So it is super resolution. It's reminiscent of super resolution factor, but there's an important difference. Instead of M, we have M diff, and M diff is the size of the coarray. It's not the size of the sensor array. Okay, so this is a very important distinction. Now, what does this result tell us? This result tells us something very interesting. Suppose you were to randomly pick points from the feasible set, okay? Feasible set, which is the intersection of this non-negative orthant and this quadratic constraint, right? So if you were to pick points randomly from the feasible set, they will obey this bound. So the set is actually bounded. The intersection of these two sets is bounded fundamentally by this quantity. As the correlation estimation error goes to 0, this set shrinks to a single point. It also tells us that, right? And this actually controls, this 1 minus rho over rho controls how the covariance estimation error affects the worst case reconstruction error. So the worst case algorithm just going to be picking points from the feasible set, not minimizing anything, right? And it also gives us a benchmark, because if just the feasibility test can achieve this kind of a bound, a sophisticated algorithm better beat this bound, right? The reconstruction error produced by a specialized algorithm should do strictly better. Otherwise, I can just, just randomly pick points from the feasible set and I'm done, right? So this is a very interesting benchmark that we obtained as a byproduct. Now, also notice that this thing tells us that covariance estimation error gets scaled by this factor n over m diff squared. Now, here the role of sensing geometry comes into picture. So if you have a ULA, uniform array, so you organize your sensors uniformly, this m diff will be theta m, some constant times m, typically 2m, 2m minus 1, okay? Then you have n over m squared, and n is typically larger than m, right? So you strictly have noise amplification. This correlation error will strictly amplify. However, if you have a nested array, then the covariance estimation error will scale by n squared over m to the power 4. So actually, instead of expansion, you can even expect contraction as long as your grid size is no larger than order of m squared. So if your grid grows linearly with m, your correlation error will not get amplified, right? This is what it tells. But if you make your grid finer, yes, then it will again start amplifying. So this is something that you will not get if you do not exploit correlation prior. Very concrete, okay? Now you may ask, your thing indicates that, the error kind of is quadratically growing in the grid size. As you make the grid finer and finer, it is growing quadratically. Is this scaling tight? Very, very natural to us, right? Because anyway, I'm picking points. How do I know that, maybe the actual achievable error exponent should be n to the power, I do not know, 1.8, 1.9. How do I know it is going to be 2? 2 can be a loser bound. So actually we show that this bound is also tight. How? We actually construct 2 points in that feasible set and show that, of course, their upper bound is governed by this n square, but they're also lower bound. The distance between them can be lower bounded by a function which is of this form, where this constant only depends on m, and this guy grows as n square. So this bound is actually tight. So if you do a feasibility test, this is the worst case performance, tight worst case performance that you will have, okay? And okay, so just to show you some phase transition plots, here on the x-axis, we plot the number of sensors, y-axis is sparsity, and we actually test correlation aware algorithms. We actually tested something called correlation aware lasso and plotted its probability of success, okay? So white denotes success, black denotes failure. So S and M, how does S scale with M? That's the point here. And here we plotted the same phase transition curve for MMVBP, multiple measurement vector basis pursuit, okay? So as you can see, here the phase transition profile, if we did it for even longer, you will see a very nice quadratic trend. It is not linear, okay? It has a quadratic trend. So we overlay this kind of a curve here, whereas this guy definitely has more black boxes, black pixels. So it fails much earlier at a much smaller value of sparsity, but this can actually tackle much higher values of sparsity as indicated here, okay? So this is another byproduct of using correlation aware techniques, that you can actually operate in a sparsity regime which is very high. Again, at the cost of temporal measurements, mind you. And this is support recovery, empirical support recovery performance versus sparsity. Again, so the left-hand plot is this correlation aware curve is in red, and the others are non-correlation aware. So you can see that they fail at a much smaller value of sparsity. On the right-hand side, I'm comparing different types of correlation aware techniques, okay? One of them is very famous, sparse Bayesian learning. And sparse Bayesian learning actually utilizes correlation to solve a type 2 maximum likelihood problem, okay, through expectation maximization. So it is very hard to analyze that problem, but if you observe its empirical performance, it's so beautiful performance, okay? This is the best performance right now among all these correlation aware techniques. So other techniques are M-focus and SPICE as well. You can make them correlation aware. Okay. So now that we talked about super resolution on the grid, the discrete version of the problem, let's go beyond the grid and let's go to the parameter estimation problem, right? Because parameter estimation problem occurs when you have point source localization, and the point source's locations gets translated into spatial frequencies, and you want to estimate those spatial frequencies, okay? So our signal model is something like this. This omega k's are the spatial frequencies that you want to estimate. And this A omega k, A is called the steering vector of the array. So if you consider this problem in the context of DO estimation, this A omega will be the steering vector of the array corresponding to the spatial frequency omega. And CKL will be the time varying amplitude of the kth source. Okay, so at different values of L, the CKLs I will consider them to be statistically uncorrelated, independent actually. And for different values of K, they are statistically uncorrelated. That is the assumption. So the goal is to estimate these parameters. So right now, I'm not trying to reconstruct an image on a finer and finer grid. I only have a fixed number of parameters that I'm going to estimate. This is a different setting than super resolution imaging over a grid. Very important distinction, okay? Because in the other case, I'm actually trying to guess as I'm making the grid finer and finer what those unknown values will be. So I have many more unknowns to estimate, correct? From a fixed budget of measurements. Here, I'm actually estimating K numbers. Well, if you are also estimating the powers and the noise power and the source powers, 2K plus 1 numbers. So this problem size is not growing, remember that. So in this case, to estimate omega Ks, naturally, you should not expect noise amplification if you have a good algorithm. There's an important distinction between noise amplification in discrete super resolution or in super resolution where you're trying to reconstruct a larger and larger image versus parameter estimation. So, so there are recently, like I said, atomic norm or TV norm minimization based techniques that tackle this problem as follows. So let's say if you have a point source model, the sources are located at tau k's. So they consider that they assume that they have access to frequency domain measurements of this signal xt. Okay, how do they collect the frequency domain measurements where there is you can pretend you have them, or if you really want to ask the question, then there are some concerns, and you can read these recent papers by Dmitry Batankov, Ayush Bhandari, and Thierry Blue, and also by Chen and Ankur Moitra, who basically say that this frequency domain measurement problem is an approximation. It is not the problem from the first principles, and there are valid reasons why they argue like that. However, if you think that this is a good approximate model, you may want to work with it, and all the atomic norm and TV norm minimization literature routinely works with this model. So let's work with this model and see what we get, what kind of guarantees we can have. Because remember, this is also the classical array processing model for harmonic retrieval or DOA estimation. So in this case, just like your steering vector, the set of all steering vectors, as you continuously vary omega, in this case tau actually, will generate this atomic set. Okay, atomic set. That's what they call the atomic set. We call the array manifold in array processing, but this is also called the atomic set A. Now, the atomic norm is basically defined as the infimum of all t, such that if you scale this convex hull of A, so if you work with the convex hull of A and you scale it by a factor of t, the smallest such t for which x gets inside this set, x belongs to this set, this stretched convex hull, that will be called the atomic norm of x. It is also the gauge function. This gauge function becomes an atomic norm if the atomic set has certain properties, which in this case it has. Okay, that is why the gauge function becomes a norm. Now, this TV or atomic norm minimization rely on something called a separation condition between the spikes or sources. And this is really important. You cannot avoid this separation condition, otherwise you don't have any theory. Okay. What is the separation condition? Typically, again, constant over m, where m is the number of sensors. And again, this is wraparound distance. Because we are working with phases, we have to talk about wraparound distances. So this is a latest guarantee. They have previous guarantees also, but this is their sharpest guarantee so far. So this is by Gongo Tang and his student. So the noise is assumed to be zero mean Gaussian with independent entries and variance sigma. If the above separation condition holds, the complex amplitudes have approximately the same magnitude. And this z is actually a weighted L2 norm. So the weight vector and the regularization parameter lambda are suitably chosen. Then you can actually show that the error in the tau will be of this form. Okay, so it will be proportional to sigma and this square root of log m over m to the power 3 over 2. So it is good. It is a good scaling, because as you increase m, you should expect your performance to become better and better. Whether it is optimal scaling or not, unknown currently. And this is the amplitude error. Amplitude error, as you can see, is function of square root of log m over m. All right. The point here is the separation condition, which is in the red box, is actually needed by these kind of algorithms, even if you do not have noise. And number one. Number two, is it a proof artifact, or somebody can come up with a better analysis of TV norm minimization tomorrow and get rid of this separation condition? No. There are negative results which show by Fernandez Granda and Max and Da Costa and Weidai that for atomic or TV norm minimization to work, this separation condition has to be satisfied. Okay, so it is not an artifact, because if the separation condition is violated, you can create situations where the TV norm minimization cannot unambiguously identify the two sources. Okay, it may actually declare one source instead of two sources. It can happen. There are examples like that, even in the noiseless setting. So now again, let's ask what is the role of additional measurements available due to the temporal dimension and role of correlation prior. Okay. And our goal will be to fundamentally relax the separation condition and also show that separation condition is not just a strict hard condition which only depends on the number of senses. It has more structure to it. It is more complicated quantity. It should depend on the signal to noise ratio, because indeed, if there is no noise, there should not be any separation. This is absolutely well established in array processing literature. You can show this very easily. Okay. So why will I need separation if I do not have noise? So there is something missing in the analysis, right? Which is where, okay, if I have separation condition, I can tackle noise, but I do not need it. Well and good if I have it, but I do not need it if I do not have noise. So can we actually come up with a more explicit characterization of the separation condition that brings out the role of SNR, brings out the role of temporal snapshots and so forth? And to do that, I will like to remind you that how sparse arrays try to do super resolution. Okay. So if you have physical array, which has this kind of a correlation matrix, you can show that if your physical correlation matrix corresponds to a sparse array, is that collected by a sparse array, then this measured correlation matrix can be written as S times T diff times S transpose, where S is a subsampling matrix, a row selection matrix. Okay, it selects certain entries of T diff. And T diff is a Toeplitz positive semi-definite matrix. What does T diff represent? T diff represents the covariance matrix if somebody had given you a long virtual array which corresponds to the difference set. So T diff is a proxy covariance matrix, which is not the measured covariance matrix, but using RYY, you can construct T diff using a linear operator. Actually, it's a linear function of RYY. Okay. Now, the point is, can we use T diff to reconstruct the omegas? And this is what I did in my earlier work on sparse arrays anyway, but the analysis was not there quite, because analysis was asymptotic. And all existing analysis of sparse arrays is asymptotic. So this is the first non-asymptotic result that I will share with you in a moment. So this is the kind of the result that I have. So this is very fresh. So the point is, suppose you have k sources and this result holds even if the number of sources is greater than the number of senses. This is very important. And this is non-asymptotic, because you see, we explicitly tell you a lower bound on L for which this result will hold. We don't say, oh, L goes to infinity and we have small perturbation and all that, okay? So if your minimum singular value of your Khatri-Rao product is larger than your noise divided by the minimum signal power, this is very important. Minimum signal power determines whether you can stably super resolve or not. Then your coarray esprit, so we actually use esprit algorithm, will lead to stable reconstruction of your frequencies, provided your number of snapshots is larger than a threshold L0. And if it is larger than a threshold L0, then as you make epsilon smaller and smaller, the L has to be increased proportional to 1 over epsilon square. Okay. So this condition, this minimum singular value condition, can actually be massaged and simplified to yield a separation condition. So what I mean is, if separation condition holds, this will hold. But this can hold even if separation condition is violated in some sense. So this is a stronger condition, okay? And the separation condition that we can get out of this will not just depend on MDiff, but also depend on this SNR. This is very important, because it will show that when you have noise going to 0, you do not need separation. It'll actually fill in that missing blank. And there's number of snapshots. We also show that number of temporal measurements has to be large enough, in particular larger than the threshold, so that we can get this kind of stability guarantees, even in the regime where the number of sources can be greater than the number of senses. So here are some plots. So it's the number of snapshots versus the DO estimation error. Blue is nested, red is ULA for 2 different separations, okay? So here separation is 0.3. You see the 2 curves are kind of close, and as the snapshots increases, they will get closer and closer. But if you have separation, you decrease the separation to 0.01, you see the gap between the performance. This is very revealing. Okay, this is a thing that's been noticed over and over again empirically in sparse array literature. Excuse me, I'm sorry. Similarly, if you increase the number of sensors, you also notice a similar trend. Okay, so this is very important, that this nested array always exhibits lower error compared to the ULA with the same number of sensors. And here are some representative music spectrum plots. So your SNR, signal to noise ratio, is decreasing as you go up along the rows, and the separation is decreasing as you go left to right. Okay, so this is basically highest SNR and maximum separation, lowest SNR and minimum separation. Okay, so blue is nested, red is ULA. So you can see there are situations where nested array can resolve two sources, but ULA fails. There's also super resolution capability that beyond the resolution limit, nested array can operate. Okay, and some concluding remarks. Again, people ask me this question all the time, that in nested array you are actually trying to estimate correlation values of the virtual measurements which have higher variance. Doesn't it affect your performance? Yes, it should. But if you do sample covariance estimation, yes, these errors can pile up. Okay. However, if you look at the Khatri-Rao bound, so this is what I will going to just show you, and then I'll conclude the talk. If you're going to look at the Khatri-Rao bound of your estimation error, so let's say we are plotting two kinds of Khatri-Rao bounds. One is where we try to form the virtual covariance matrix. We parameterize the problem, so that this is the only unknown parameter, the entire covariance matrix. Okay, and here in the other case, the parameters are the omegas and the p's and sigma. So let's try to understand how these two Khatri-Rao bounds behave. So this is the result we recently presented at SLOMAR. So if you look at the covariance estimation error, okay, then the nested versus ULA, nested array, the CRB and the ULA CRB, ULA is actually below the nested array. So this is expected that the covariance estimation error of ULA must be smaller than the covariance estimation of the nested array. These are for only the elements that are shared by both, okay, because nested array has additional elements. However, if you look at the frequency estimation error, the trend reverses. The red curve is above the blue curve now. Blue curve is nested. So this shows something very interesting, that fundamentally, although there is more error in the covariance estimation, they can potentially be compensated in the DO estimation stage. And this is a question that I'm very interested in. And I think this will really address some of very insightful and interesting questions in coarray processing, which does not arise if you do not work with coarrays. Like if you work with ULS, you will never get into this kind of situation. So concluding, I just want to say that noisy super resolution is a challenging task. Utilization of appropriate priors can make a significant difference. And to best utilize the priors, one should use sensing geometry and algorithm should work hand in hand, okay, not one without the other. And in using optical instruments and optical systems, you can actually implement the sensing geometries. So optics people do it all the time, actually. Not the way sparse array operates, but changing the point spread function of the image using grating lobes. It's not using diffraction gratings and masks and so on and so forth. You can actually play around with the point spread function of your optical imaging system. So there are a lot of ways in which you can engineer the system. And resolvability of point sources depends on both spatial and temporal measurements. And if you know how to use temporal measurements properly and utilize the priors, you can achieve higher resolution. And right now I'm working on generalizing this for different other kinds of point spread functions. Thank you very much. And that concludes my presentation.
Okay, thank you, Piya. So I think we're a little bit over time, so I take 2 or 3 quick questions.
Yeah, absolutely. Yeah. And I'm here. I can hang out even after the scheduled time. I'll be happy to take more questions.
Okay, so yeah, I'll first forward the one question from the chat box. Rohan Pote asked that is the stable recovery bound an artifact of the optimization problem being solved by Candice?
Oh, that's a very good question. So I think you're asking about the super resolution factor, right? Yeah, so let me.
I think the first stable recovery.
Correct, yeah. Yes, I'm going there. Yes, I see. So let me tell you. So to answer this question, I have to go back to Donahoe's paper, okay? Which I did not discuss here, but I'll tell you in short what the answer is. So in his paper, Super Resolution by Sparsity, Donahoe actually shows that if you look at worst case error amplification, okay, it can be characterized by something called the modulus of continuity, okay? And the modulus of continuity itself has a lower bound and an upper bound. The upper bound of the modulus of continuity is something like this, little bit different because the exponent is different for n and m, okay? The power is n cubed divided by m squared, something like that. Lower bound is n over m. It's not n over m squared. How to achieve the lower bound? Unknown currently. So in that sense, you can say that it's probably an artifact of the algorithm, but does an algorithm exist that can actually attain the lower bound of the modulus of continuity? Currently unknown, unfortunately. Yeah. And I have a recent paper, this ICASP, I did not get the chance to talk about it. I actually also look at the Krammer-Rao bound for noise amplification, for understanding noise amplification. So the Krammer-Rao bound actually shows but remember these two are different notions. Donohue is talking about worst case, Krammer-Rao bound will be the mean square error, okay? So we have to be cognizant of that. So the mean square error will also show noise amplification, but the exponent is something like 1.5, okay? But the setting is slightly different than Donohue's setting because there we also use the correlation prior and so forth. Yeah. So the model is slightly different. But in the Donohue's case, if you look at worst case error, do not make any statistical assumption on the noise, bounded noise, let's say, then you will get the exponent will be the lower bound of the modulus of continuity is scales as n over m. And the upper bound is slightly different than this. So it is somewhere in between, I must say. Yeah, sure.
I have a quick follow-up. So you're deriving the Krammer lower bound for this problem, but did you show that your estimator is unbiased or?
No, you cannot show that the estimator is unbiased because whether the estimator is unbiased or not, that's not an easy question to answer. Yeah.
That's what
for especially for this kind of convex problems. No. So if your estimator turns out to be unbiased under suitable conditions, then your Krammer-Rao bound will be a valid lower bound for that. But in general, no, we cannot say that. Even in the paper by Stoica and Nehorai, the very seminal work on music maximum likelihood Krammer-Rao bound, all these estimators are at best asymptotically unbiased. If you have finite SNR, finite snapshots, you cannot say that they're, even music is, you cannot say that it's unbiased.
Have you considered the minimax bound?
Yes, I have looked in the minimax bound, and for the minimax bound, you have to again look at the worst case error, right? The worst case error and the worst case parameter setting and the best estimator for the worst case, right? Right. So it will be a slightly different statistical model in that case. Yeah, maybe bounded noise model.
Yeah, very nice. Any other questions from the audience? I shouldn't take all the opportunities. Okay. So you could unmute yourself. Yes, To.
Yeah, go ahead.
So I would say that's a sort of a minor question. So is there any reason why you chose L1 norm to measure the error here? So like,
okay, yeah, I did not choose. This was actually Candace's result that I'm quoting here. So because his optimization is like this, y minus QZ L1 norm. So he's minimizing the L1 norm, not the L2 norm. Okay?
But I also recall that in some of your own results, you also presented those with L1 norm. Correct.
So if you change the norm, because you see norms are related by inequalities, right? So in the worst case, there could be a extra scaling factor if you change the norm. So changing the norm may actually change the bound. It's not that obvious unless you can show that these results have some sort of an isometry that these norms are close to each other, right?
Yeah, so exactly. I was wondering, like, is there any reason? Is it because you want to get like the optimal dependence on dimensions?
Yeah. So let me tell you, the point is whatever norm you choose, be consistent and then compare across those norms. Yeah. Don't mix apples and oranges. I must say that. Yeah. Correct. Okay. So if you choose L2, L2, then compare L2, L2. So L2, L2 RIP may not be same as L1, L1.
So my question is, like, if you choose L2, L2, so if you compare L2 to L2, do you get the same scaling factor?
You may not get the same scaling factor because again, you have to look at, suppose you go via this technique. Of course, you can bound L1 norm by L2 norm on both sides, and you can get a loose bound. But whether you can get a tight bound or not, no, I'm not. That's a good question, but yeah, it's not obvious.
Okay. Yeah. Sure. Thanks.
Yeah.
Okay, folks. I think we're over time, so I think it's a good time to wrap it up. Let's thank our speaker again. Thank you, Piya. Thanks a lot.
Yeah, thanks a lot. And I'm here. I mean, I can hang around and listen and take more questions if you want. But if you do not have any question, thanks a lot for the opportunity to talk. These days I give 2 lectures every week, so I get to talk a lot. But it's not the same as in-person interaction. So,
sure.
so I'm very happy to kind of see friends from the community and my fellow colleagues from.
Especially when you're giving classes and sometimes students do not respond that much, and you're like,
yeah.
Okay, thank you, folks.
Right.
So
Sure.
let me remind you. Next week, our seminar is on the New York time, Pacific time Thursday, and Hong Kong time Friday morning. And we will be sending you reminders if you have subscribed. And our speaker will be Professor Vangelis Papalakisakis at the University of California, Riverside. We will be talking about tensor decomposition and the graph data mining. Fantastic topic. So I hope to see all of you next week. Thank you for being here.